Swayam Prabha. Digital India. Educated India.
Now, today I will start a new topic, that is the design of shallow foundation. So, here design means I will discuss about the how to decide the dimension of a shallow foundation. I mean, what would be the length, width, and what would be the depth of the foundation. And in my previous modules, I have discussed that what are the different types of field test by which we can determine the soil properties. Now, today I will discuss how we can use those properties to design the foundation. Then I have discussed the bearing capacity calculation, settlement calculation. Then in the fourth module, I have discussed about the concept of beams on elastic foundation. Then not only settlement and the bearing capacity, if we want to determine the bending moment and the shear force, how we can determine those properties as well as the deformation by considering soil and the foundation interaction. Now, today first I will discuss the bearing capacity and the settlement checks, and then we will decide the dimension of a foundation based on the field test data as well as the laboratory test data, because as I mentioned that for the sandy soil field design of the foundation on sand soil, we prefer to use the field test data, and for clay soil, as we can collect the undisturbed soil sample. So, we can use the laboratory test data for the design of foundation on clay soil. So, I will discuss the design of foundation of shallow foundation resting on sandy soil by using field test data, and then the design of foundation on clay soil by using the lab test data, because in as I mentioned that for field test data for clay soil we have to use with caution, because the field tests are short term test, but the clay soil behavior of foundations are long term. For example, the plate load test data. So, that plate load test data test is short term, but the as you know that the consolidation takes very huge time for clay soil. So, those field test data for like plate load test in case of clay soil, you have to use them with caution. But so, that is why we will use the design of foundation and clay soil by using the lab test data. So, first I will discuss that plate load test design, that we have the first example problem, that following the data was obtained from a plate load test conducted on 60 centimeter square plate at a depth of 1.5 meter below the ground level on a sandy soil which extend up to a large depth. That means that it is a homogeneous soil. So, we can use this data, but as you know that for the layered soil also we have to use this data, this field plate load test data with caution, because we in the plate load test, which is a small scale test compared to the our actual foundation. So, if there is a layered soil, then there is a possibility that in case of plate load test, that for a particular layer may not be influenced by the plate load or test, but actual foundation those data may be influenced due to the load coming on the foundation. So, in those cases you have to use these data cautiously, but here it is homogeneous soil. So, we can use this data for our real foundation also. So, determine the settlement of a foundation 2 cross 2 meter carrying a load of 500 kilonewton placed at a depth of 1.5 meter below ground surface on the same soil. So, the depth of foundation for the plate or the depth of foundation and the depth of plate both are same, and then but one case the plate size is 60 centimeter, but actual real foundation size is 2 cross 2 meter square, and then we have to determine the settlement of the real foundation if the foundation is subjected to a load of 500 kilonewton. Okay, so now these are the plate load test data. That means we apply the load and we measure the settlement. So, I have discussed already the what is plate load test during my discussion on settlement of shallow foundation. So, now today I will use that plate load test data to decide what would be the settlement and if that settlement is sufficient or not for that particular dimension which is chosen based on that plate load test data. Now, this is the load intensity is given from 50 to 400 kilonewton per meter square and settlement is given 2.5 millimeter to 46 millimeter. And based on that we have drawn a load versus settlement curve. So, this x axis it is here it is load intensity, which is kilonewton per meter square, and in the y axis it is settlement, which is in millimeter. Okay. This is drawn. Now, we have the area of the real foundation is 2 cross 2, that is 4 meter square, and the load which is applied on the real foundation is 500 kilonewton. So, the load intensity that is equal to 500 divided by 4, which is 125 kilonewton per meter square. Okay. So, the load intensity of the foundation is 125 kilonewton per meter square. So, as I have discussed that this settlement that we will get for the plate as well as the foundation for the same load intensity. Okay. So, that means the load intensity that is coming on the real foundation that we will use to determine the settlement of a particular plate. Okay. So, that means here the load intensity is 125 kilonewton per meter square, and so the corresponding settlement of the plate is 125 will be, this is 100. So, this is will be 125. So, corresponding settlement will be around, this is 6.5 millimeter. So, the settlement of the plate is 6.5 millimeter corresponding to a load intensity of 125 kilonewton per meter square. But that settlement is the settlement of the plate, but we have to convert it to settlement of the real foundation. So, how to convert that? So, that conversion techniques. So, you know I have given. So, it is on the clay soil. So, for the clay soil the settlement of the foundation is equal to settlement of the plate, then BF, then width of the foundation, then BP plus 30 divided by BP, BA plus 30 to the power square. Okay. So, B is the width of the foundation, BP is the BF is the width of the foundation, BP is the width of the plate. So, now the settlement of the plate is 6.5 millimeter and width of the foundation is 200 centimeter, because this in this equation 30 is given. So, 30 means this BP and BF should be in centimeter. So, actual dimension of the plate is 2 meter cross 2 meters. So, it is 200 centimeter. 200 centimeter, then plate dimension is 60 and then 30 plus. So, then it is 60 200 plus 30. So, that is whole square. So, this settlement is 11 millimeter. So, the settlement of the plate under a load of 500 kilonewton or settlement of the foundation under the load of 500 kilonewton is 11 millimeter. So, what we have done? We have taken the loading intensity, the corresponding to same loading intensity to determine the settlement of the plate, then we converted it to the settlement of the foundation by using the available correlations for sandy soil. Okay. But here the effect of water table is not considered, because here the water table effect is not considered. So, this is the first part of the problem. So, now the second part, what would be the actual settlement if the water table is at the base of the foundation. So, now initially in the first part the water was not present, in the second part water is present at the base of the foundation, then what would be the settlement. Okay. So, in the second part, so water table effect. So, here suppose this is your foundation and foundation depth is 1.5 meter from the ground surface, and in the same depth the water table is present. So, we have to apply a correction factor. So, that correction factor is Cw. So, Cw we know that we can write 0.5 dW by B. So, here we are using the recommendation given by IS code. So, Cw is that, because I have given the two types of correction factor determination. So, here I am using the correction factor suggested by the IS code. You can use the other one also. I have given two of them, but here I am using the IS code one. So, this IS code, because why I am taking the IS code? Because IS code, it is given that if the water table position is within the ground surface and the base, all the cases it is 0.5. So, that means, if the water table is at the base of the foundation, then also it is 0.5. If it is base of the foundation, ground surface, then also it is 0.5. So, that means, within the ground surface to the base of the foundation it is 0.5, but other correction factor you will find that at the ground surface it is 0.5, but at the base it will not be 0.5, it will be slightly higher correction factor. Okay. So, but here I am taking as the IS code, but it will give me more safer design, because as the correction factor is 0.5, which is the lowest correction factor. So, that means your bearing capacity or the will be reduced by 50% or the settlement will be increased by 2 times. So, that means that is why I am taking the IS code, but you can take the other one also. But here I have taken the IS code recommendation. So, but here the DF value as the IS code, the DF is calculated from the base of the foundation. So, basically DF is calculated from the base of foundation. So, here water table itself at the base of foundation. So, the DF value or dW value, this is dW value is calculated from the base of the foundation, and here dW is itself is 0. So, that means we can write that this is 0.5. Okay. So, if the Cw is 0.5, so actual settlement of the foundation will be, without water the settlement was 11 millimeter, and as I have discussed that if it is a settlement, you have to increase the settlement, because settlement will increase due to the effect of water table, and bearing capacity will decrease due to the effect of water table. So, in case of settlement, we have to divide it by the correction factor, because as the correction factor is less than 1. So, that means the actual settlement considering the water table effect is equal to 11 divided by 0.5. So, this will be 22 millimeter. So, the actual settlement considering the water table effect is 22 millimeter. So, it is increased by 2 times. Okay, so, this was the one part of determination of the settlement. Now, suppose you can see that this 22 millimeter which is within the tolerable limit or not. So, if it is within the permissible limit, then your dimension is fine. The dimension that you have chosen for that particular load is fine, but if it is within not the permissible limit, then you have to change the dimension. So, this is one way to choose the dimension of the footing. So, that means initially you select one particular dimension, then determine the settlement based on that dimension of the foundation. Then you check whether that settlement that you are getting within the permissible limit or not. If it is not within the permissible limit, then you have to change the dimension. In other way also, suppose your permissible limit for example is 50 millimeter and you are getting 20 or 25 millimeter, then you can change that settlement to make change your dimension of the foundation to make your design more economical. So that your permissible settlement and the settlement that you are getting should be close to each other. Okay. So, that is why here I do not know what is the permissible settlement, it is not given in this particular problem. So, we are just only determining the settlement, that is 22 millimeter, and we hope that this settlement is within permissible limit. But there is a alternate way also you can use this platelet test data. Suppose in that case your example problem 2, because this is your example problem say 1, in example problem 2 here permissible settlement is given. Okay. Permissible settlement say which is given is 50 millimeter. Okay. So, and this settlement is considering the water table effect. So, that means you can see if we do not consider the water table effect, and for example, why I am talking and we are applying this correction, that means when your plate load test was conducted, that time this water was not present there. So, that is why you have to consider this water table effect. So, that means the plate load test that is given where the water table was not present, so or water table was far below the plate depth. So, that is why water table effect not incorporated or was not within the data that you are getting by this plate load test. But now, if in case the water table position is in the base of the foundation in actual case, then how the settlement will change. So, that is the question. So, that means here the permissible settlement is given 50 millimeter. So, that should be within considering the water table effect. So, but we cannot compare this permissible settlement directly with your plate settlement, because plate settlement is done without considering the water table effect, but permissible is we have to consider the water table effect. So, actually we have to consider the lower settlement value, so that when we apply the water table effect, so that settlement will reach to the permissible settlement. Okay. For example, in initial case, initial problem without water table effect, the settlement was 11 millimeter. Now, once we apply the water table effect, then the settlement is 22 millimeter. So, now your 22 millimeter should be less than 50 millimeter. Now, because permissible settlement is given. So, that means we are going an alternate way. Initially, we know the loading intensity and we determine the settlement. But now, in the second solution case or second problem, we know the settlement and we will determine what is the maximum loading intensity or safe load intensity we can apply on the foundation. So, it is totally the reverse case. Initially, loading intensity was there and we determine the settlement, then we check whether that settlement is within permissible limit or not. And second case, permissible settlement is given, Now, we are determining what is the shape load that particular foundation can carry. Okay, so, this is the permissible settlement. So, settlement to be considered will be 50 into 0.5 or CW. So, this is 50 into 0.5 equal to 25 millimeter. So, why we have now multiply it with 50 settlement, because now 25 millimeter will compare with the our plate settlement. Now, for example, if I take 50 the total settlement, then definitely the settlement of the plate will also be more. Okay. And if the settlement of the plate is more, then the loading intensity will also be more. So, but actually we have to take the 50% of the permissible settlement. For why? Because our correction factor is half. That is why you have to take the 50% of the settlement, such that, so that means this settlement is 25 millimeter is without considering the water table effect. So, that settlement now we can compare with the plate load test data, as the plate load test also conducted without considering the water table effect. Now, this 25 millimeter settlement, now if I consider the water table effect, that will reach to 50. Okay. So, that is why we have taken 25 millimeter. Now, we will compare this 25 with the plate settlement. Now, then the same conversion we have to use. Now it is settlement of the plate is settlement of the foundation into BP, BF 30 divided by BF, BP 30 square. So, this is 25, then 60, then 200 plus 30 divided by 200, 60 plus 30. This is 14.7 millimeter. So, corresponding 14.7 millimeter is around here. So, corresponding value is around this is 220, around 235. Okay. So, this value is around 235 kilonewton per meter square. Okay. 230, it will be 238 around. So, this will be 238 or 14.7 around 235, yeah, that will be fine, because 14.7 will be slightly higher side. So, this will be slightly upper. So, it will be 235. So, now if we take 50 itself, then this value will be around 30 millimeter. So, if I take 30 millimeter, so loading intensity will be around 320-25 millimeter. So, that means that 325 millimeter, if I consider total 50 centimeter, so that will be without considering the water table effect. So, you can do in the other way also, but it is better to apply the correction factor in the settlement and then calculate your loading intensity. Okay. So, that means if I take 325 millimeter kilonewton per meter square, so that will be higher without considering the water table effect. So, and if I consider the water table effect, the bearing capacity will reduce. So, that is why we are taking the lesser settlement value considering the water table effect, and then we determine the loading intensity, and that is giving 235 kilonewton per meter square. So, my Q safe or Q allowable, that is will be 235 kilonewton per meter square. Okay. So, this is also one way we can determine the allowable bearing capacity. Now, you check that or under this dimension you can apply this much of loading intensity on the foundation, and you check whether that loading intensity is sufficient or not. If it is not sufficient, then you have to change the dimension. Okay. So, this is the two approach by which we can decide what will be the dimension of the foundation based on the plate load test data. And one more thing I want to mention, that here the depth of the plate and the depth of the foundation both are same. So, there may be a case where the depth of plate and the depth of foundation, they are not same. So, suppose your depth of plate, obviously the depth of foundation should be more than the depth of plate. Okay. So, in such case, that you have to apply the depth corrections. The depth corrections, how you will use the depth correction, I have already discussed during my settlement calculation part, but I will also show in one of the example problems in this or next classes. Then you have to apply that depth corrections in this settlement value. Okay. And the difference of the depth will be your depth of foundation in such case. Okay. So, that means what would be the depth of foundation in such case? Your difference of the depth between the plate and the real foundation will be the depth of foundation. Okay. So, next problem that I will discuss, that suppose in sometimes we can conduct two plates with different sizes. What is the purpose? To minimize the size effect, because as I mentioned that we are using the small size plate load or plate to conduct the plate load test. So, there is a size effect is there. So, to minimize that, we can use the two different size plates, and then based on that plate load test we can determine what would be the actually dimension of a footing. So, this is the example problem. The two plate load tests were conducted at the level of a prototype foundation. That means, here also depth of foundation and depth of plate both are same, which is actually the ideal case. Is same in same cohesionless soil. This is also sandy soil, and the following data are given. Now, the size of the plate, one is 30 centimeter cross 30 centimeter, where the for 25 kilonewton applied, 25 kilonewton applied load, settlement is 25 millimeter, and for 6 centimeter cross 6 centimeter plate, 75 kilonewton applied load, settlement is 25 millimeter. Okay. Now, we have to determine the dimension of a square footing, that if we apply 1000 kilonewton load and we will get the same settlement. Okay. So, that means, we have used the two different plate on the same soil, different plates, and one plate is given 25 millimeter settlement under 25 kilonewton load, another plate is given 75 kilonewton 25 millimeter settlement under 75 kilonewton load, because its plate dimension is 60 cross 60 centimeter square. Now, we have to determine by using this plate load test data, what is the dimension of a real footing if we want to get the same settlement under 1000 kilonewton load. So, in the next class, I will solve this particular problem, that how we can use these two dual plate or two plate load test data and to determine the dimension of a footing.